In the last lecture, we were dealing about polarization. Now, let us get into boundary conditions for electric field. So, first of all, what is basically boundary conditions? Till now, we were discussing about the electric field inside a particular medium, like whether it is epsilon 0 or epsilon 1. Epsilon 0 means free space, or epsilon 1 meaning dielectric. So for a particular material only, not two materials together. So that is the major difference here. Now we are getting into two types of materials together. So that is the difference. Right, and we before in the last class, or not the last class, the class before that, there we saw what happens for the electric field intensity inside a conductor also. So now let us get into the electric field, the conditions of electric field where when it comes to the interface between the two media, right? Like I have a medium 1 where my electric field intensity is E1, and I have another medium where my electric field intensity is E2. So what can we say about this interface between two media? What will be the electric field density at at those points, or on the surface, or on the surface between the two media? So that is what we are going to discuss. So what is boundary condition? Boundary condition means the conditions that the field must satisfy at the interface separating the media. They are called boundary conditions. The conditions that the field must satisfy were at the interface between the two media. They are called as what? Boundary conditions. So let us get into how we can find out, right? First of all, before getting into how, let us see the possibilities that we are having when we say two media. What all kind of media we can? We can have two dielectrics, like I am having rubber here, and on the other side I am having mica. They both have different dielectric constant. Like here I have epsilon 1, here I have epsilon 2. So that forms what? Dielectric-dielectric interface, right? Dielectric-dielectric boundary conditions are possible. So that is one where you have two types of dielectrics with the two dielectric permittivity values, right? What is the next possibility? Next possibility is when you have a conductor and you have a dielectric. So that is the second possibility. There, that also we will see what happens to field inside a conductor. We have already seen, right? So what will happen when you have a conductor and a dielectric interface? Right, like a copper and a copper wire inside, which is a conductor, and above that you have a dielectric of PVC. What happens at the interface? So that is our second type of possibility. Now we let us get into third possibility. What is the third possibility? We can even have conductor and free space, right? So these are the three possibilities where we are going to define what we are going to define our boundary conditions. So let us get into now let us see how we can find how we will be able to find out the field at this points, where at the interface between these points. For that, it is quite simple. Again, before that, let us get into why we are concerned about this, or why we are going to see what is the condition of the field at the boundary between two media. The interesting part is that if the field on one side of the boundary is known, then we can find out the field on the other side of the boundary. Like if let me say in the conductor I know the field, then what will be in the dielectric side, or in one dielectric I know the field and I know the how the field is varying. Then I can determine what will be the field on the other media. So that is the major application of this thing, or why we are doing this, why we should find out the boundary condition, or why we should be deriving this. The reason is this, that once we know the field on one side, we can easily determine the field on the other side, if and only if we know what is the boundary condition, or what is the field condition at the boundary between the two media, right? Now the procedure is quite simple. We are going to apply Maxwell's equations at the boundary. So when I say Maxwell's equation, This let us refresh this equation. It is about potential, means E dot dl equal to 0 over a closed loop, right? If this is a loop I am considering like this, if this is a closed loop, over this closed loop and some field is over the surface, or not surface, or through that some field is there, some electric field is there. So under that condition, if we see a closed loop, then what? Then over the line, this closed loop E dot dl will be equal to 0, right? This we already learned before in our electrostatics. The another one is also familiar to you, the Gauss's law. What Gauss's law states? Gauss's law states that d dot ds equal integral over the surface integral. If we have a closed surface, if we have a closed surface like this, then whatever be the d is the electric flux density coming out, then Gauss's law we already know that d dot ds will be equal to what? The charge enclosed inside the closed surface, right? Charge enclosed by that closed surface. So that these two equations we know, that is what we are going to apply. Another part that you should be knowing is that let me erase this part. Okay, yeah, another part that we should be knowing is that the decomposition of electric field density and electric flux density. Electric field intensity and electric flux density, they are just have a difference of what? They are just multiplication of what? Permittivity. We know that d the electric flux density is equal to what? Epsilon times the electric field intensity. So, and this electric field intensity or flux density, I am showing here electric field intensity only, means E here. So this E can be decomposed into two vectors like tangential component Et as well as the normal component En. So if we apply Et plus, if I take the En and keep it here, Et plus En will give me vector E as per triangular law, right? Et in this direction and En in this direction. If you add up, you will get the vector of vector E, right? So these are the concepts that we are going to use to find out what the boundary conditions involved. Now this is how we will be using like the vector E equal to Et plus En and D equal to dt plus Dn. Et or dt means the tangential component of electric field intensity or electric flux density. En and Dn means the normal component of electric field density and electric flux density. Clear? So now let us get straight into this boundary. Let us see the dielectric boundary conditions. So there we have got two mediums, right? This the first one as I have drawn here, the first medium. Now this is the second part, the two medias. What is the difference between these two media? These two media major difference is that their permittivity are different. One is having a permittivity epsilon 1, another one is having a permittivity epsilon 2. That is the difference between these two dielectrics. Both are having different permittivities, right? So definitely the electric field inside each of the material will be different, right? Electric field inside the electric field vector will be different in the two types of material. Let me say on the first medium, let me say vector E1 is the electric field intensity, right? Vector E1 is the electric field intensity. Then as I told you before, we can decompose this vector into E1t as well as E1n like this. Similarly, you will have a vector E2 in the medium 2, that also you can decompose as what? E2t and E2n, the tangential and the normal components, right? It is like tangential to the surface or the boundary between the two mediums, understood? And normal component is normal to the boundary between the two mediums, okay, clear? Now what we are going to do is that first part is that the path we have to consider a path. As I told you before on how, means how to find out boundary condition, we will apply what? We will apply our Maxwell's equation. One is what? E dot dl equal to 0 over a closed loop. So for that I am considering this closed loop here in the red one, in the direction with the arrows prescribed A, B, C, D, A. That is my closed loop. So there that closed loop is very thin. Let me say this delta H here, which is what that is the height of this box, right? This height is tending to 0, that much small, so very small. And our main assumption is that along that path our electric field density is not varying with respect to the space, with respect to space coordinates. Our electric field density is not varying in that small distance, means wherever you take, your electric field density is going to be constant, right? That is our assumption. That assumption is valid when your box is so small or your delta H is tending into 0. That time your assumption is valid, and that time it is somewhat becoming the surface also, right? Surface between the two media also. So now if we apply E dot dl equal to 0 along the loop A, B, C, D, A. So first we have to go from where A to B, right? First we have to go from A to B, and where this AB portion of this loop, where this AB portion is in medium 1, right? This AB portion is in medium 1. So this A to B, that portion is where this is in medium 1. So and it is having a permittivity epsilon 1, and we know that our electric field is even in where medium 1. And since we have decomposed into tangential and normal components, this tangential component will be along what AB direction, and normal component will be along the BC or DA directions, BC or AD directions, right? So now let us see how we will write the equation for the E dot dl. Okay, first let us consider the AB. For AB, what is the component of electric field density? It is E1t, right? The tangential component which is in the direction of what? Which is in the direction of AB, right? So E dot dl means what? Which whenever you have in the same direction, you can just multiply. So the normal component will not come for AB. So E1t into delta W, where delta W means what? Delta W of this is the length. If it is delta W here, here also it is delta W only. So delta W is the length. So E1t into delta W is the dot product for E dot dl in the portion A to B. From B to C, we have two portions, right? Up to here, up to here means B to in between B and C, half portion. So that length will be how much? Delta H by 2, only the half portion of B to C. Total BC is delta H only. Only half portion is what? Delta H by 2, and there your what is the what is the even fraction which is in the direction of this BC? That is your normal component, right? So E1 into delta S by 2 will be the dot product in the area where from B to till the surface, right? From B to the boundary, from this B point to the boundary point, from B to this boundary here, from B to boundary, you will have what? E1 into delta S by 2. And if after the boundary to C, from boundary to C, here again what it is? E2n into, because here what is the field? E2n, right? Whichever is the normal component. E2n into delta S by 2 will be your normal component. Now see here we have given negative. Why? The negative sign here means that BC you are coming in which direction? Let me erase some part here. Okay, BC you are coming in which direction? You are coming in this direction. BC the length is the delta S by 2, or the delta H is in this direction, and your field is in which direction? E1 and is in the opposite direction. That is why you have given negative here. Even when you came from the boundary to C, from boundary to C also when you came, that time also your E2n means the normal component in the medium 2, that also is in the opposite direction. That is why we have placed negative on these two components, minus E1 n delta S by 2 and minus E2n delta S by 2. Okay, then the remaining part is what? Remaining part is minus E2t into delta W, right? That means what? C to D, what will be the condition? C to D, the direction of that length delta W is in this direction, and your tangential component is in the opposite direction. So your here also you will have negative dot product. So it is minus E2t into delta W, plus again what? Just as similar to this side, you will have plus E2n delta S by 2 plus E1n delta S by 2. Here your field as well, the normal component of field as well as the line means our DL direction also is the same. So that is why you got positive here. Now that is how we wrote what E dot DL equal to 0 for this loop. You can try for yourself once. So once you have written this, here one interesting part is that E1 n into delta S by 2, here you have a negative part and here you have a positive part. So that cancels. Similarly here minus E2n into delta S by 2n plus E2n into delta S by 2. So that also gets cancelled. So what we get, so remaining part is E1t into delta W minus E2t into delta W equal to 0. So we get into this equation. So if we take out delta W, we get that E1t minus E2t into delta W equal to 0. Since delta W cannot be 0, we can say that what E1t minus E2t will be equal to 0. E1t minus E2t equal to into delta W equal to 0. What we understand is that E1t minus E2t into delta W equal to 0. So what it implies? It implies that E1t should be equal to E2t, right? Or in words, we can say that our tangential components of electric field intensity are the same on the two sides. E1t means tangential component of electric field intensity on the first medium and E2t means on the same in the second medium. They both are same at the boundary. That is what it means. Or we can say that ET undergoes no change on the boundary. At the boundary between the two medium, there is no change on tangential component when you are having two dielectrics. Or in another words, it is called, we say that the electric field density's tangential component is continuous on the boundary. Means there is no change on the boundary for ET. Even right, understood. So that is the main point. Now, as I said earlier, electric field density and electric flux density are related. How? As D equal to epsilon E, or D equal to epsilon E. It is just getting multiplied by the permittivity, right? So that same electric flux density also can be decomposed that dt plus dn, right? So we already got that E1t equal to E2t. E1t means what? E1t in terms of d we can write as d divided by epsilon, right? D equal to epsilon E means E will be equal to d divided by epsilon 1. So tangential component of E1t will be equal to what? D1t divided by epsilon 1. Similarly, E2t will be equal to D2t divided by epsilon 2, right? So this is the another boundary condition, condition at the boundary for tangential component. Means here what it means, you anyhow, since this permittivity is coming into picture, D1t and D2t are not going to be equal. Understood? Tangential component of the electric flux density is not same at the boundary between the two media. Because of what? Your permittivities are different. So when your electric field densities components are same, then definitely flux density will not be same because the permittivity values are different at the different media, right? So d1t by epsilon will be equal to d2t by epsilon 2. What it implies is that dt undergoes change at the interface. Understood? The electric field intensity's tangential component Et is not having any change, and so it is continuous. But dt, electric flux tangential component dt, that is not continuous or it is discontinuous at the interface. Clear? Be very clear with it. Electric field intensity's tangential component is continuous and electric flux density's tangential component is discontinuous. Clear? It is if one is continuous, then the other one should be discontinuous. That is the way it goes. Tangential component of field. Now let us get into what the normal component. For that, we now before we consider electric field intensity, now we will consider electric flux density. D1 is decomposed as D1t and D1n. We already know about what D1t, right? We already discussed about D1t. So similarly in the second media you got D2. It is also decomposed as D2t and D2n. So and here what we are going to apply is that we are applying the Gauss's law. Gauss's law means what? Surface integral over d dot ds equal to the charge enclosed, right? So we are going to apply Gauss's law, and for that we are choosing the small cylinder, the plit box. That's the small cylinder. It is having a curved surface as well as a circular area on top as well as bottom, right? This top bottom surfaces, its area is delta S. I am calling it delta S. Okay. Now what happens? When we take d dot ds, again, since we already have decomposed it into d1t and d2t, if you take on the first media, on the curved surface, if at some point you have this d1t and so, let me say here you have a small differential surface. So if you take that normal component and you got d dot ds, let me say on this surface, just opposite to that, you will have a place where your the same similar d is coming inside, and you have the delta s is in the opposite direction. So on this curved surface, or the curved surface means for everything you can consider as a circle inside again. So there what we will have, there you will have d dot ds equal to 0 over the curved surface. If you come to the next medium also, same happens. If you have a d dot ds a component along this one, here also here that d dot ds component will become negative on the other side, just geometrically opposite to that. So similarly on the curved surface you will not have any dot product of what, d dot ds. So we only have to worry about what, or the top as well as bottom surfaces of this cylindrical box or cylindrical Gaussian surface. Clear? Now if we take that, what is the flex density which is normal to this delta S, that is the normal component of the flex density d1n, right? So if we write equation, let me say on the surface we deliberately place some charge delta q. Okay, that is the charge enclosed by this the cylindrical Gaussian surface. On this small surface, I already placed what, on the boundary, I am already placing some delta q. Then let us first concentrate on d dot ds. What is the d dot ds component? It is d1n. d1n means what here? d1n into delta s, because delta s direction is what? Normal outward. Area's direction is normal outward. So d1n, the normal component of electric flux density in the first medium, and the delta s, both are having the same direction. That is why here it is d1n into delta s. The dot product is just multiplication, d1n into delta s. And but on when you come to the second medium, your field's normal component is what, again in the same direction as your same direction as your field direction in the first medium. But the surface delta s, as it is normal outward, what happens, both are in the opposite direction, and you have what, negative sign here, minus d2n into delta s. This is your d dot ds, which is equal to what, the total charge enclosed. If at all there is some charge is enclosed and you have a surface, right, delta s is there, and here our assumption is that delta s tends to 0. So what we are making it deliberate is that we are placing delta q at the boundary, and that surface area is, let me say, is delta s again. So our the total charge can be written as what, surface charge density into delta s. So it is rho s into delta s equal to d1n delta s minus d2n delta s. I think it is clear. So under that condition, we can what we can write, when under this condition, d1n delta s minus d2n delta s equal to rho s delta s, right? So if we cancel delta s on the two sides of the equation, you will get that d1n minus d2n equal to rho s. Understood? Means what? The normal component of electric flux density which is entering through this side, right, minus what, whichever is coming through the other side, d2n on the other side, the difference between them will be equal to what, the charge density. Understood? The difference between them will be equal to the charge density at the boundary. That is when we know that there is some charge at the boundary, right? Now we already know that there is no charge at the boundary, means what, the rho s value is 0, means we already know that our boundary is charge free, there is no charge density at the boundary, and then in that condition d1n minus d2n will become 0, or we can say that our normal component of what, electric flux densities are same. Understood? It was the reverse for tangential component of flux density. Here we can say that d1n equal to d2n when our rho s equal to 0. This is another boundary condition. So the normal component of D is continuous across the surface. The normal component of D is across the surface. Before what we got, the tangential component of D is discontinuous at the surface, right? So it is vice versa here. So the normal component of D is continuous across the surface. So that is another boundary. That with that we we have got the all boundary conditions in what dielectric boundary. Okay. Now let us see conductor dielectric boundary condition. Means what? One is a dielectric, means the whatever I did not draw, this part I am calling it as dielectric, and you have a conductor, right? You have a conductor. Here this epsilon value is not there. Why? Because you need not be conductor considered. You have a conductor here. In my second lecture, in module 4, we already discussed the condition of electric field density inside a conductor. What is the electric field density inside a conductor? E will be equal to 0 inside a conductor. We already see what is the reason also. Why we have why we have the electric field density 0 inside a conductor? Because our conductivity becomes more tends towards infinity. We had a discussion about that in our second lecture. So electric field density is 0 inside a conductor. This is the fact that we are going to exploit to find out the boundary condition in the case of a conductor dielectric case. Okay. So we want to find out the boundary condition. Now at the boundary, let me say let me say in the dielectric, our electric field density is what? E, as shown here. It is decomposed into two components, ET as well as EN. Okay, at the boundary. So now what is the way to do this? Just as before, first we will consider a loop A, B, C, D. Here I have considered it reverse. You can see whatever way you want, A, B, C, D, and we will find out what? We will find out the we will see what happens in Maxwell's equation. So around this closed loop A, B, C, D, A, our E dot dl will be equal to 0. So that is known. So let us see how E dot dl across this loop. So when you see here A to B, the AB part, right? This AB part, this is inside the conductor, and we already know that electric field inside the conductor is 0. So there is no question of normal or tangential component of electric field. Everything is 0 here inside the conductor. So I have written 0 into delta W. That corresponds to the section AB. When you take B to the surface, B to the surface means again what? That also is again inside the conductor. No tangential, no normal component of electric field density inside the conductor. So again what? 0 into delta S by 2. The other part, the other delta S by 2 from the boundary to C, means in the inside the till the dielectric. That part, their electric field density is there, and there our normal component is En, which is in the direction of what? This BC. So we got En into delta S by 2 as the dot product E dot dl. Right. Now the CD part, as we know, delta W is the width. So in the CD part again your tangential component is there, but tangential component is in this direction and CD is in the opposite direction. That is why we have a negative sign here, minus ET into delta W. Plus again what? En into delta S by 2 will come, because this is again in the dielectric, not in the conductor area. So En is the normal component and the delta S by 2 the surface. Right. So delta S by 2 is the surface part. So you will have plus En into delta S by 2. Clear? Then okay, one mistake I did here is that this is not plus, this is minus, because En is in this direction, En is in the upward direction, and your DA is in the downward direction, right? So I have to write it that way, En in delta S by 2. Again, when it comes to this boundary to A, again, when it comes back to A, that small area, that is where, that is inside the conductor. So without doubt we can write 0 there. So 0 in delta S by 2 equal to 0, right? There is no much difficulty in writing that E dot dl equal to 0. So from that what we understand, what we we have all from that what we can understand, here there is an En in delta S by 2 positive part, and here is a negative part. I wrongly wrote positive here, very sorry. So E plus En into delta S by 2 and minus En into delta S by 2 cancels out. So only left part is Et into delta W, and that Et into delta W equal to 0. Since delta W cannot be equal to 0, we can just write that what the tangential component of electric field intensity, the tangential component of electric field intensity at the boundary between a conductor and a dielectric is 0. That is our first. Now let us apply the next part, means what? Let us apply Gauss's law using the cylindrical Gaussian surface. It is also quite simple, right? Inside, when I say electric field density is 0, what is flux density? D equal to epsilon E. When E is 0, epsilon, whatever value you got for epsilon, what will happen? What will happen? Inside a conductor, the electric flux density also will be equal to 0. So in the last case, as we have already discussed, on the curved surface there will not be any dot product. So only on the top and bottom surface it will be there. On top surface we have a normal component dn. So that is what this dn into delta s means. But on the bottom surface, since it is inside the conductor, there is no electric field density. So we wrote it as 0 into delta s, or what we directly get is what? D delta q equal to dn into delta s. Or we can write dn equal to what? If we take delta s to this side, dn equal to dq delta q divided by delta s, which is the surface charge density on the boundary, right? So here your normal component at the boundary is equal to what? Surface charge density, right? The surface charge density. So that is the direct direction here, dn equal to rho s. This is the boundary condition for normal component. From it is easy to get the complete boundary condition. So this point, let us conclude. So this point we already discussed even in the first lectures itself, that no electric field may exist within a conductor. Inside the conductor there is rho s equal to 0 and electric field density is also 0. This we discussed very clearly in our second lecture, right? And that is inside the conductor, right? And there can be no potential difference between any point on the conductor also, right? That is when you say it's same field, right? So there can be no potential difference also. Now in terms of the boundary condition, what we can say is that an electric field must be normal to the conductor, right? What we got when we find out dn we found it as what? Rho s. So there is a which component? Normal component of electric flux density, or we can say that there is a normal component of electric field density also, because it is just multiplication. So epsilon r en equal to rho s. So that exists, and every time when you see a conductor and a dielectric, on the conductor on the boundary you will have a normal component of electric field density as well as electric flux density, and you will not have any tangential component of what? Electric field density or electric flux density, because we already proved what? Et equal to 0. Since Et equal to 0, epsilon r Et also will be equal Et, which is equal to what? Flux density is tangential component, that also will be equal to 0. So these are the boundary condition when you are when you are considering a conductor dielectric boundary condition, when you are considering a conductor dielectric boundary condition, right? So that's an interesting thing, that you only have normal component and you will not have any charge inside the conductor, or rho s will be equal to 0 and electric field density also will be equal to 0. This particular property, it is having an application which is called electrostatic shielding or screening. So as you can see here, you have a conducting surface. This blue surfaces are what? Conducting surface, let me say. So in conducting surfaces, so inside the small volume A, you have another smaller part B. In between you have something, let me say, and outside you have C. Okay. So normally you have some charge here and you have some charge here, and if A is not here, definitely the field inside B will be affected by what? The C, the C part. But now since we have this A in between, and as you can see it is earth, so earth, right? So you have got a boundary between C and B, having what? This metallic part. Here you have a conductor, here let me say dielectric, again one conductor and dielectric. So because this what happens is that B and C are become completely isolated due to the presence of this A. Why? When you have this A, so as you already know, electric field inside is 0. So whatever happens on this portion due to C, that is not getting affected inside, right? So that is why here that effect is not known also. And because of B, definitely the field here will change. Because of B, the field here might change, but that effect is not getting propagated to the outside this A due to the presence of this A. Understood? Because again the field is not changing based on B inside this metal. It is always 0. It is just independent. So B and C are completely isolated due to the presence of A. Means A which is in between these two. Understood? So we can say that A acts as a shield or screen, and the field is completely independent inside and outside the shield. This principle is used in a lot many places in electrical engineering, so that you can check out what is the applications of electrostatic shielding or screening. Then now the last case is that we will see the conductor free space boundary condition. Conductor means what? Their electric field density is 0. What about free space? Free space just means that it is you can say as another dielectric only, because it is having a dielectric permittivity. What is the permittivity value? Epsilon 0. So it is just a special case of our conductor dielectric boundary condition. The one and only one thing you have to do is that this I think you remember this equations, right? Dn equal to for conductor dielectric boundary condition it was epsilon 0 epsilon r En, and here also it was epsilon 0 epsilon r Et, right? Instead of epsilon 0 epsilon r, since your epsilon r has become 1 because it is free space, right? For free space or air, what is the permittivity, relative permittivity? It is equal to 1. So you can just take off epsilon 0 epsilon r and you can keep epsilon 0. That much is the only difference when you are having free space and conductor. Okay, no more doubt about that. Okay, you can these equations are directly delivered from that by considering it as just as a special case of what? Conductor dielectric boundary condition. So this is about the boundary conditions. So our next class will be on magnetic boundary conditions. So, and before that I just want to conclude. In this lecture we discussed about what? Different boundary conditions. Whenever you have two mediums, then in between you have an interface, right? So at that interface surface or at that boundary, what is the field conditions? That is what is meant by boundary conditions. It can be two dielectrics with different permittivities that we discuss. There we have seen that the tangential component is what? Tangential component is continuous, right? And normal component, the tangential component is continuous for what? Electric field intensity, and because of that your electric flux density tangential component is discontinuous because you have different permittivities. Using Gauss's law we also saw that what? Dn, the Dn d1n minus d2n equal to what? The surface charge density, or the electric flux density's normal component will be continuous if you are not deliberately placing any charge on the boundary, right? And since it is, when it becomes continuous, that definitely mean that your normal component of electric field is not going to be continuous. So that is about the dielectric case. When we come into dielectric and conductor boundary conditions, there we have to just see the fact that same application. We have to just see the fact that inside electric field, inside the conductor, electric field equal to 0. So we got that Et will be equal to 0. Tangential component of electric field density will be equal to 0 in a conductor dielectric interface. Even in conductor free space also it is the same only. There only normal component of electric flux density or electric field density will exist. So that is the main point when it comes to conductor dielectric or conductor free space boundary conditions. Okay, conductor free space boundary condition means it is just a special case of conductor dielectric boundary condition where we are just changing the epsilon 0 epsilon r value with epsilon 0 because your relative permittivity is 1 for free space. So this is about boundary condition. It is quite easy to learn. Just sit for some time and write down the boundary condition by yourself or derive it by yourself. It will become easier. Answer the review questions which are there along with this video uploaded. Okay, so thank you. We will see the next lecture. Next lecture is on magnetic boundary conditions. Next lecture is on magnetic boundary conditions. So that we will discuss on the next class. Thank you.